All right, this next section is about how our atmosphere is heated. Now, generally speaking, our atmosphere maintains a rather mild temperature when we kind of compare it all the way around the globe and stuff. Yes, there are extremes, hot and extreme cold in some places, but overall, it's pretty mild. How does our planet get heated? Well, that's mostly in the form of solar energy or solar radiation. Two names, same thing. This is energy from the sun. Yes, there are geothermal energies and such, but those are such a small percentage when compared to the amount we get from the sun. The atmosphere obtains heat from the solar energy that reaches the Earth, and this is what drives our weather. We get this heat in the form of radiation. We will see this term again because I want to combine it with some other terms. But radiation is the transfer of heat by electromagnetic waves. Electromagnetic waves are waves that include radio waves and light waves. Electromagnetic waves include a lot of things, including X-rays, cosmic waves, cell phone waves, TV waves. It's a very broad spectrum. However, the amount that actually gives significant heat isn't as big. We have another term here, insolation, which simply stands for incoming solar radiation. And that's the main driving force behind our temperatures and weather here on the Earth. It is usually measured in watts, the amount of energy that something gains, loses, or uses in 1 second. If you look on some of your electronic devices, you will probably see some kind of notation about how many watts per second or watts per minute it utilizes. Microwave ovens are pretty much sold that way. If you go through Walmart and you look at microwave ovens, that will be a major feature on them. Sometimes sound systems as well. We'll talk about how many watts they're using. If you go outside your house, you can see a dial somewhere on the building that shows how much electricity your house uses in terms of kilowatts per hour, thousands of watts per hour. There are several factors, I believe we're actually going to talk about 4 factors that affect insolation. One is cloudy weather, reduces the amount of insolation. And that's because of a term I actually forgot, which was on the last page, I believe. I accidentally skipped over it. Number 5 there, albedo. This is the decimal equivalent of solar radiation reflected by an object. All objects either absorb or reflect solar radiation, and depending on coloring, depending on makeup, will change how much they absorb or how much they reflect. If you have a dark colored car, it can get pretty hot on a hot day. A lot of solar radiation is absorbed by the darker colors. And a light colored car sitting in the same place for the same amount of time will actually not be as hot. It still might feel hot, but it won't be as hot as that dark colored car. Now, because of albedo, that's why clouds really affect insolation, because clouds have one of the highest albedos. Actually, it might even be the highest albedo of 0.7, reflecting back almost 3/4 of the sun's radiation back into space. Another factor that affects this is the length of daytime. Just the amount of time that light is or radiation is hitting the Earth. In the winter, we get short days. The shortest day of the year is the winter solstice, usually around December 21st. And then the longest day, or period of daylight, is the summer solstice, which I believe is around June 21st, if I'm remembering right. One of the last factors here that we're going to talk about is the Earth's distance from the sun. The Earth's closest point is perihelion, because the Earth does not orbit the sun in a perfect circle. It's more of an oval shape. So there is a period where we're closest to the sun, period when we're farthest from the sun. Perihelion is that closest point in 2011. That was January 3rd, 91.4 million miles. The aphelion, not aphelion, but aphelion, is Earth's farthest point from the sun. And on 2011, that was July 4th at around 94.5 million miles. So yeah, these are all factors that will affect insolation, which will affect the temperatures. One reason why the winter weather is much colder. And again, I think I accidentally skipped one there, which was the angle of the sun's rays. During December, because the Earth is on a tilt, its axis is tilted. It is not perfectly perpendicular to the sun. There are periods of time when the amount of sunlight is spread over a larger area. In December, that's what's happening. The amount of sunlight is spread over a much larger area, resulting in cooler weather, less temperature because it's spread out more. In June, the same amount of sunlight is in a much smaller area, resulting in higher temperatures, more insulation going into an area. So those are our 4 factors there. And those things affect the Earth's energy budget. How much energy actually reaches the Earth's surface and is not reflected. Energy that enters the Earth's atmosphere and is not reflected. Because the clouds are between the ground and the sun, that can play a huge role. Now, Earth's energy budget is not the same everywhere we go on Earth. Obviously, different places of the planet are at different angles to the sun because of that angled axis. And as a result, we do have an uneven distribution of sunlight and radiation throughout the planet. Also consider that half the planet's dark and half the planet's light at a time. Again, uneven distribution. Now, something that kind of counteracts that uneven distribution is the greenhouse effect. And this is the process of trapping heat near the Earth's surface. There are several greenhouse gases. The 2 of the more important ones are water vapor and carbon dioxide. There are several others. Our graph here mentions methane, nitrogen dioxide, and then it says others. And as you know from our study of the composition of the atmosphere, really the only one on here that has any significant composition in our atmosphere is carbon dioxide, even though it's only at what did we say it was? 0.003% on average, I think. The other ones are barely mentioned. We talked about water vapor being highly variable depending on a few factors. Humidity was a measurement of that variability. And the most important and abundant greenhouse gas is water vapor. Why? Because water is heated more slowly and it releases heat more slowly. It actually can hold a lot of heat energy for quite a long period of time. And we'll kind of look at that again here. But when I looked for a graph including water vapor, I found 2 right away on Google Images. And because a lot of the other ones don't include water vapor. And here's the reason why. A lot of environmentalists don't consider water vapor when they're talking about the greenhouse effect. Now, the greenhouse effect is a desirable effect. Again, it keeps our planet moderate temperature-wise. If we didn't have the greenhouse effect, as soon as the sun went down, we would lose all that heat, and it would be downright frigid at night, possibly to the point of not being able to survive it. But because of the greenhouse effect trapping that heat down here, it keeps even the evenings a little bit milder when the sun is not there. Some of that heat is still trapped. So yeah, a lot of environmentalists don't talk about water vapor. Why? Because water vapor is not something man controls in any significant amount. Notice from the graph that it's probably well over 90%. The person doing this did not use percentages in showing this. He was just trying to show comparisons. And carbon dioxide is the next largest, but we already know that's only 0.003% of the Earth's atmosphere. It's much more significant in terms of the greenhouse effect. It has a bigger chunk of the wedge there than 0.003. But just by comparison to the other gases that have a much smaller wedge, including down to other. So, yeah, because of the greenhouse effect, the warmest part of the day occurs well after noon. Over land, it's around 3 p.m., and over the seas, it's around 5 p.m., because there's a lot more water holding onto a lot more heat and releasing it at a slow rate. So it tends to stay warmer longer over the seas. Now, how do we distribute that heat? Now that we've talked about that heat being here, and here's part of that factor there. Insulation warms water much more slowly than it warms land, and water also holds heat much longer than land does. So we can get some of these other these ways of transferring heat here. Radiation, we mentioned before, heat transference by electromagnetic waves. Conduction is heat transfer by direct contact. When this hand touches that hot handle and feels that heat, that's conduction. Convection, heat transfer by moving currents of hot air or other liquids. Any fluid can have convection currents. And these are currents set into motion by convection. What happens to hot air? It rises. Well, if hot air is rising, something has to come in and take its place. And it only rises to a certain point, then it cools off again, and then it falls back down to where it can heat up, rises, and you get these horizontal currents, or excuse me, not horizontal, vertical currents in the fluid. And that's what they show there in the boiling water in that pan. Let's see. Most of the Earth's weather occurs in the troposphere, which we already noticed, and it's because of, or as the result of, convection currents. We get updrafts and downdrafts. Both of these are vertical movements of air. The only difference is which way is the air going. Updrafts go up, downdrafts go down. I hope that will be easy to remember. Usually we really only see downdrafts during some pretty vicious storms. I mean, there can be downdrafts for other reason, actually coming off of a mountain slope where it's colder up top and coming down that'll cause a downdraft. Winds are horizontal movements of air. And this has all been about heat transfer. Now, the next few there are not about heat transfer. They do result in changes of temperature, but it's not because heat is transferring from one object to another, or from one substance to another. And that's the term adiabatic. It refers to a process in which heat is not transferred. Like I said, we still measure a temperature change, but it's not transferred. And adiabatic heating is the temperature of a gas rises as the gas is compressed with no heat loss. Backtrack just a minute to understand what temperature is. It's a measure of collision of molecules. The more collisions there are, the hotter something is. And gases have this unique ability that they can be compressed. You can't really compress solids, you can't really compress liquids. But gases can be compressed. And as a result, when you compress a gas, you force those molecules closer together, and they collide a lot more often, resulting in a higher temperature reading. Now, the actual amount of energy hasn't changed. If we were to release that pressure and let it go back to its original size, we would go back to the original temperature reading. And adiabatic cooling is the opposite of that. The temperature of a gas drops as it expands. So as we release pressure on it, those molecules can move further away, resulting in fewer collisions, and therefore a lower temperature reading. And this is exactly what happens in our weather. Insulation comes in, heats up the air close to the ground as the rocks and stuff absorb heat, radiate it back out, and the heat starts getting hotter and hotter, and that hot air rises. That's transfer of energy. We just talked about conduction and convection right there, and really radiation as well. Now, what happens as that gas rises, there's less pressure. We talked about that a little bit in the last section. And so the gases spread out until they reach an altitude where they're no longer hot enough to keep rising. The temperature has gone down because those molecules have spread out. There's no longer the amount of collisions maintaining that temperature. And eventually they spread out, they cool off because of spreading out, and then they might sink back down, and we get those vertical convection currents of air. And that goes with 13. When a body of air rises, its temperature drops because of adiabatic cooling, that reduction of pressure on the air. So, the very last thing is answer the science video question, and so that I can tell that you watched this video. Also, don't forget on Classcraft, there could possibly be gold points or experience points for this. So, make sure you also double check there.